Greetings. Welcome to the 11th lesson in a series of lessons on basics of power systems engineering. Up to this point, my presentations were about DC power and resistive circuits. Starting with this lesson, I'll be covering AC power and AC systems. I would like to start with a contrast of the graph of a DC voltage drawn versus time to that of a sinusoidal AC voltage versus time. DC stands for direct current. Any voltage or current that stays on one side of the time axis and never alternates between positive and negative values is considered to be DC. On the other hand, AC voltages and currents alternate between positive and negative values. AC stands for alternating current. The AC quantities encountered in power systems are virtually always sinusoidal and at a fixed frequency of 60 cycles per second. Notice that I said virtually because under certain conditions the frequency can deviate from 60 Hz momentarily. As well, the voltage and currents can get distorted and not be sinusoidal at all under abnormal conditions. However, the collective goal of the power systems industry is to keep the power as close to purely sinusoidal and at a fixed frequency of 60 Hz as is practically possible. I should mention at this point that frequency of 60 Hz for power systems is the standard in the United States and some other countries. Other nations have adopted 50 Hz as the operating frequency of their power systems. Let's now turn our attention to the AC signal or time function. The diagram on this page shows an ideal and clean graph of an AC voltage. I'm showing AC voltage as a point of discussion. However, the whole argument applies equally to AC current functions as well. Let's look at some of the characteristics of this function. The first thing to note is that this time function repeats itself regularly as you move along the time axis. The time it takes for the graph to start a new repetition is called the period of the function and is typically assigned the capital letter T, seen here. The number of times the cycle repeats per second is called the frequency and assigned the lowercase letter f. There is a simple relationship between time t in seconds, this time period, and the frequency f in cycles per second. They are actually inverses of each other. So we can write f equals 1 over t or t equals 1 over f. The common name for cycles per second is Hertz, which is abbreviated to Hz. Since we know f to be 60 Hz for our national power system, we can calculate the period of AC voltage or current as t equals 1 over 60, which results in 0.01667 seconds, and which can be converted into milliseconds as 16.7 milliseconds. It is common in the power industry jargon to refer to short time periods as in cycles instead of in seconds or milliseconds. So if I hear that a breaker opens up in 3 cycles after it receives the trip signal, I know that the time it takes for it to operate is 3 times 16.7 milliseconds, which comes to 50 milliseconds. So I know that this breaker operates in 50 milliseconds, which is 1/20th of a second. Another quantity associated with any time function is its average. Clearly, the average of a purely sinusoidal function, as pictured here, is 0, since it is moving symmetrically above and below the time axis, spending equal time on the average in the positive and negative territories. And here you see V average for this signal is 0. If the signal is not balanced between its positive and negative values, however, the average can be non-zero. As an example, a fault current in the power system may have an additive DC component for a short period of time, causing its average to be non-zero. Next slide shows the graph of the sum of an AC and an exponentially decaying DC voltage. The average of this voltage is not zero, but a positive quantity. Other time functions, such as the instantaneous power function, will in general have a non-zero average, which, by the way, is its real power component, which is the useful part of the power that is being produced and transferred or consumed. AC power will be covered in a future lesson. Let's look at another aspect of the AC time function. Here we see the maximum value that this time function can take. It operates between Vmax and negative Vmax. The ideal sinusoidal functions take on values that are bounded by a positive quantity and is negative. In this case, I'm calling it Vmax for positive and negative Vmax for the negative limit. In practice, however, in a power system, the maximum Vmax can gradually shift over the 24-hour period of the day, depending on the conditions governing the grid at any time. Also, at the same moment, the voltage can and does have different maximum and effective values at different points of the grid, again depending on the distance from the generation centers and conditions of the grid at the time. The idea is to maintain the voltage at any given point of the power system between relatively tight limits defined by the governing standards and not allow quick fluctuations within those set limits. The other challenge is dealing with the different voltage levels that's experienced at different points of the grid. Here, too, power providers and grid administrators try to limit these differences in voltages along the length of the distribution system and try to get the voltage profile to be as close to a flat profile as possible. I'll get to issues of frequency and voltage regulation in future presentations in this series. Closely related to the quantity Vmax is the effective value of the voltage, which is alternatively known as the RMS value. In power engineering, we almost never work with the maximum value that a voltage time function takes on, but with the effective value of the voltage or current. The RMS, or effective value of a sinusoidal voltage or current, is the magnitude of a DC voltage or current that, when applied to a resistor, will deliver the same power to it that the AC voltage or current under consideration would. This value, known as root mean square and abbreviated to RMS, happens to be Vmax divided by square root of 2 in the case of the AC voltage, and similarly Imax divided by square root of 2 for the AC current. So here we have Vrms equals Vmax over square root of 2. And if this were a current curve or current function, this would have been Imax. And IRMS would be Imax over square root of 2. Of course, we can rearrange these formulas to find the maximum quantities in terms of the RMS quantities, such as Vmax equals the square root of 2 times Vrms, and similarly for Imax. When you're given the value of an AC voltage or current in an exam or on a single line or any other document, that value refers to the RMS value of the voltage or current, unless explicitly stated otherwise. Let's now take a look at the trigonometric function that is behind the shape of the AC voltages and currents. This is the general form of a sinusoidal signal function. V of t equals Vmax times sine of omega t plus delta. You can see that Vmax right here before the sine function. Omega is called the angular frequency, and it is equal to 2 pi times ordinary frequency of f. Shown here, omega equals 2 pi times f. Imagine a point going around a circle at the uniform rate of f times in a second. Let's say in this direction, although the direction doesn't matter. Every time this point completes a revolution, it has traced an angle of 2 pi in radians around this circle. So once it has completed f rounds in a single second, it has traced 2 pi times f radians in terms of its angular displacement, which we'll call the angular frequency and give it the name omega. It is easy to see from this argument that the unit of measurement for omega has to be radians per second. Now let's attach a pair of axes to this circle. As the point goes around the circle, the height of its projection on the vertical axis, which would be this height here, traces a sinusoidal function that is seen on the right. Assuming that the equation on this page is representing a 60 Hz voltage, omega comes to roughly 377 radians per second. Seen here, calculated as 2 pi, 2 times pi times 60 for f, and that comes to very close to 377. And the unit, of course, is radians per second. Also, since this diagram shows no horizontal displacement of the graph in either direction, as you can see, it starts at 0. Delta, which shows here in the equation, should be set to 0 for the equation to truly represent this graph here. So for this graph, this delta is equal to 0, but not in general. So this equation then becomes Vmax times sine of 377t. If delta were to be a non-zero positive number, the effect would be shifting of this graph to the left by delta radians. A negative value of delta, on the other hand, would represent a corresponding shift to the right. The graph on this slide shows an AC voltage with a non-zero phase shift of delta radians. Here delta is a small positive value. The angle delta is called the phase angle of this function. And you can see that non-zero delta has resulted in this curve shifting to the left by an amount of delta. Relative changes in phase angles between principal electrical quantities such as currents and voltages are very important and have considerable effect on systems operation. In terms of time shift, delta radians is equivalent to delta over omega seconds of time shift. Delta over omega has a time unit, and that's the time shift of the graph, delta over omega. For example, if delta were 60 degrees, which is equivalent to 1.0472 radians, this would cause a time shift of 1.0472 over 377 for a 60 Hertz signal, which is about 0.002778 seconds. In terms of a fraction of a cycle, this is exactly 1/6 of one cycle. As you divide 60 over 360, the answer is 1/6. Currents too have associated phase angles. You see the equation here. The phase angle I assigned to this current time function is beta. If the voltage above represents the voltage across an AC load, and the current here represents the current through the load, such as seen on the next slide figure, I through and voltage across, then the difference between the phase angles that's shown here, delta minus beta, is called the power factor angle, and it has a direct role in determining the load power, which will be discussed in a future lesson. The cosine of the power factor angle is called power factor, and it is usually abbreviated to PF. The name power factor carries with it the importance of this quantity in determining power transfer to the load. Power factor is always between 0 and 1, and it will be called leading if beta is greater than delta. It will be called leading, and it will be called lagging if beta is less than delta. Effectively, leading means that the current leads the voltage in its phase angle, and lagging also means that the current lags the voltage in its phase angle. We have reached the end of lesson 11. The topic of the next lesson will be on the use of phasors in working with voltages and currents in AC circuits. This is Fuad Albandi, founder and instructor of the educational group Own Your Destiny. If you enjoy watching my channel, please click on the subscribe button and the notification bell. You can also visit my website at the link shown on this page, own-your-destiny.mylearnworlds.com. Thanks for watching this video, and I hope to see you in another one of my presentations.